talk. Today, I'm going to be talking about some of the research I've been doing at the University of Melbourne. In particular, we're trying to look at nuclear magnetic resonance, which is a common technology used in spectroscopy techniques, in MRI, things like that, and trying to see if we can link music to it in some capacity. Now, I'll explain in detail how the two are linked, but what we want to try and do is see if we can recontextualize this technology through musical theory, and then try and figure out whether we can get any information from that. So I'm not insinuating that there are going to be certain molecules that prefer Radiohead or something like that, but who knows? Maybe sometime down the line we'll find out that Beatles are objectively the best music because all the molecules really like it. Who knows? But long way away. We'll get to that when we get there. So I just wanted to go through a little mind map of the links that we have to make in order to get to the final product. So first thing we're going to talk about is how do we actually get information about molecules using NMR. So the general idea is that when molecules are placed in a magnetic field, they tend to align themselves in a particular direction. And not only that, they end up spinning with a certain frequency. And when we match this frequency with, say, a radio signal or something like that, they resonate and they produce a signal that we can measure. And the difference in this response changes based on where the chemical is within its own chemical environment. So I've got some examples of some of the results that you would see in a typical, MRI spectrum or something like that. This chemical here, benzene, it has 6 hydrogen environments, all that are all identical. And so when we get our final result, we only get one particular resonant frequency. Whereas we look at something like ethanol, we have this OH group here, these 2 hydrogens here, and then these 3 hydrogens here produce 2 separate groups, each with their own defining frequency. And so you can map that and from there work your way backwards to the chemical structure. So it's quite a powerful technique. It's non-invasive. You don't have to extract whatever molecule you're looking for from its natural environment. Lends itself really well to looking at natural specimens in vivo, and it's quite high resolution, which is really good. But it is quite insensitive and often requires you to run your sample multiple times in order to get an appropriate result. And furthermore, it's often not quite fast enough to be able to look at dynamic events. So for an example, we'd want to be able to look at things like protein folding. This is something that's still a very big active area of research. We want to know what happens when a protein moves from its folded state to its unfolded state when it's increased in temperature, all sorts of things like that. So there are some things that we want to work on, and music may potentially be the answer. So now we're going to talk about the link between NMR and music. So 2 key characteristics I want to talk about. One is this idea of timbre. So timbre is the distinct sound made from any sort of musical source, and it's the characteristic that allows us to differentiate between, say, my voice and then, say, playing something on my trusty piano over here. Don't worry, you'll see more of that in a sec. And this is the basis for any sort of signal construction. You put together different contributions of all these frequencies to make a distinct sound, whether it's the piano, violin, your voice, whatever. And so these musical sources are just frequencies that we can apply to molecules and stimulate them. So that's cool. That's all well and good. The other thing we want to look at is this idea of tuning. So there is no objective right or wrong. When someone talks to you and says that you're out of tune, it's sort of very subjective because you have to assign a particular tuning system to base your things off. So, but the point is that we can do that, and that based on whatever tuning system you use. So I've got a little keyboard here. This is based on something called 12-tone equal temperament, where you've just got 12 notes, they're divided equally that's how we do it. And then we have a reference note based on a certain frequency. That's how you define everything else. And so you can have frequencies that are either on or out of tune with these frequencies. Going back to what we were talking about before, each of these chemicals and their different environments has its own frequency. And so we can also define a tuning system and then thus define a pitch for each of these chemical environments. So for example, I've got the molecule ethanol here, and we've got our 3 different chemical environments. Please let me know if this is too loud, but bear with me. So we've got our first hydrogen here, our second hydrogen over here, that's G, and then our hydroxyl group, the OH, can be represented by an A sharp. And then together, we can think of it as a G minor chord in musical lingo. But the point is, we can think about these molecules as having their own pitch. And then likewise, when we start to analyze and apply musical signals to them, we can see how far in or out of tune we are with respect to the molecule. So now we can start talking about the research that I was trying to do, which is trying to emulate the response of an NMR signal and then be able to apply musical signals to that to see how they would respond. And what basically happens is you can think of this idea of being in or out of tune with respect to a particular chemical is it's similar to something like it's similar to what's called a bandpass filter, which is a common tool used in things like electrical engineering and audio production that allow you to take in a certain range of frequencies and then tune out everything else. So now what we can do is we can take our NMR spectra of our ethanol here and then reimagine it as a bandpass filter where each peak is representing our different notes. So this could be our first hydrogen group, the second one, and our hydroxyl group. And through this method, we now have an alternative way of describing what is normally quite a complicated physical system, lots of maths, lots of nonsense, which I won't bore you with, into something that is perhaps more intuitive to think about and could perhaps allow us to oralize our chemical results. So this is what I did for the majority of my research. So we take in our NMR data, our chemical information, we collect whatever audio we want to apply to it. I wish I could have done it for you in real time, but my simulation involved being able to input music in real time, which would have been great. But alas, we won't be doing that today. Then we go through the process of actually constructing this bandpass filter, and again, won't bore you with the details, but the final result is a bandpass filter that mimics the response that these molecules would have were they put in an NMR spectrometer. So here I've got an example. Now going back to our ethanol case, we've got our D, G, and A sharp represented by these 3 peaks here. And these are representing the individual chemical environments represented in that molecule. And so what happens is if we play something that has those notes, the output that we get will not change. Whatever we put in will come out exactly the same. Anything that strays too far away from that will be dropped down in volume, and then we'll hear basically nothing. So I've got some examples here. Now I'm going to play some more audio. A couple of them are going to be quite quiet. Don't worry if you can't hear it. I'm more concerned if it's going to be too loud. So what we've got here is a couple of examples where I've played a musical signal that exactly matches our molecule, and then played one that is far away. And so we end up getting an example of maximum resonance or maximum in tuneness, where we get our full signal. So this is the unfiltered version. And then we play the filtered version, and we see that we basically get the same thing back. And then if we look at an example where I play something further away from those resonant peaks, and then feed it through the filter, we hear basically nothing. And you can see this represented on this little plot here. This yellow is our original signal, and then our blue one has been diminished to basically nothing. So that's all well and good, right? But we're not really here to listen to boring little sine waves. We want to actually play some music and see what's going on. So as a sort of final piece for this research, I put together a big list of molecules. Don't worry about all the stuff on the table, it's just there for reference. And I've constructed a bandpass filter from all of these molecules. As you can see, it looks quite complicated and messy, but the point is we've got one peak for each different chemical environment. And what we have now is this molecular ensemble that picks out little bits of frequency here and there. And now what we're going to do is play a cover from one of my favorite bands, The Police, and we're going to see what happens if we were to play this to these molecules in an NMR spectrometer. So here's the unfiltered audio. I'll have to check if there's any Police fans in the audience. Might need to change the song in later times to appeal to the audience. But anyway, here's the filtered audio. You can see it's already quite quiet. But you can see we've lost quite a lot of the top end. You don't hear a lot of the really high notes, and everything sounds quite muffled, but we can still hear something, which is still really interesting. This is the data for some of it, but it's basically telling you the same thing, that the level of detuning based on what our musical signal was is giving us different information, and this could be an alternative method for retrieving chemical structure. And not only that, it provides an alternative, it provides an avenue for recontextualizing this physics system into something that's more easily understood. So all in all, this musical NMR idea is a really cool alternative simulation method, which sort of simplifies, again, this complex process into something quite straightforward, more or less. And begs the question, you know, are molecules prone to certain keys? Is Coldplay the best band of all time? Who knows? They only went to Perth, so I mean, you know, there's a little bit of bias there from me. I'm a bit disappointed. Anyway, but through this level of detuning based on what molecules prefer what, it provides options for alternative methods of learning about chemical structure. Machine learning is quite a big area where if we can gather enough information from lots of different known sample structures, we may be able to learn something about chemicals in a much quicker, more efficient way. And I think equally as important is this idea that it's quite an educational and communicative tool. I know personally from my own experience learning physics, one of the adages quite often used is just trust the maths, which as someone who's never been that good at maths is very poor advice. So I'd like to think that using this description of this physics system provides an alternative means for people, not just students, but other laymen, people in people in the industry who just want to get a grasp on the quantum realm that's sort of taking over with things like quantum computing and stuff like that. So maybe in the future, this is the way that you'll learn about NMR and other physical principles. Thank you for listening.
Thank you so much, Jake. Everyone, round of applause for Jake's fascinating talk. Wow, we've already had quite a few comments come in. Some people are keen for you to use the Bluey theme song, which has a broad demographic of parents and children and everyone in between.
I should have done that. Yep, that's the optimum pick. I should have done that.
Yeah. Tony Cam says that the music visualization of molecules is fabulous. Patrick Capon says on slide 9 or 11, does that transition from NMR spectrum to musical frequency plot mean that you lose the integration data from the NMR?
Hang on. Let me bring these slides.
Look.
What was it? Slide 9.
9 or 11. The
9.
NMR spectrum to musical frequency plot.
I think this one probably. Yeah. Okay. Sorry. Where was the question? Everything's going everywhere. I can't figure out.
It's does the transition from NMR spectrum to musical frequency plot mean that you lose the integration data from the NMR?
Um, not necessarily. There was a bit of working around with picking things like sample rate based on what sort of audio signal you were using. Um, there is the sort of issue that something I sort of glossed over is the response that the molecules gave you isn't necessarily in the audible spectrum. But this is something that can be easily, up or down shifted based on what we need, and could still provide a sort of one-to-one correlation between what the molecules are doing and what we can hear. So yes, there is this factor of how long you're exposing the sample to for with our music, other conventional things that come up with NMR, but that's probably something to involve with in later work, where I'd really like to flesh out this model more and see, try and get some more quantitative measures of information that we can get. So I hope that answers the question.
Yeah, Patrick, let us know if you have any follow-up questions. We have a comment from Janina Nakajima Castro, who says this looks like an interesting way to make data more accessible for those who are blind or visually impaired. And they've seen data converted into music by the Chandra X-ray Observatory.
Oh, that's interesting. Yeah, I hadn't really crossed my mind. I mean, there's a reason why I was so interested in this project to do at uni. I've been very much struggling to decide between pursuing science or music. So, and I very much believe that, I think, relating back to Chris's talk, that there is something inherent about music and the spirituality of it all, that there is some missing piece that science doesn't have that I think would be very valuable in the method of communication. So barring the sort of physical nature of accessibility, I think this has the potential to be quite an intuitive measure of this physical phenomenon. And of course, if you've got perfect pitch, you might be taken on by NMR researchers to be able to listen to our samples to tell us exactly what frequencies are going on. But keep your ear out, so to speak.
Interesting stuff. Wes Ward says, does chemistry plus math equal music? Let's go.
We're hoping so. I think that would be the dream. I think it's still got a way to go in terms of taking that final leap back from this musical output to chemical structure. But it's a very real possibility that, well, I'm not saying that if you go get an MRI anytime soon, they're going to have Led Zeppelin playing through the speakers, but maybe something to that effect might allow for a more efficient method. So, fingers crossed.
Fantastic. Tony Ken says, can we use it in the school classroom? And if we were to, what would we need to do to make that happen?
Well, the simulation is quite straightforward in that you would only need to look up your chemical data online, and there are many resources that are publicly available that you can check to look at the different frequencies for a particular chemical, and then I during my research I was considering trying to implement the work through things like digital audio workstations, things like GarageBand and Ableton and stuff like that. So I know those sorts of things are very widely applicable, and that it could be used to sort of simulate a molecular effect, if you will.
Okay, great. Tony says he's going to give it a go. Indigo has said that they love the creativity and exploration in this project. How did you correlate the NMR resonance with a pitch? Was it a choice? Curious too if you've played around with different NMR field strengths, e.g. 400 megahertz versus 800 megahertz.
Yes. Okay. So good question. I as I was sort of saying before with the whole idea behind tuning, can everyone still see my PowerPoint slide? Yep, I think so. Okay, cool. Yep. Yeah, so like the same, what I was talking about with tuning, it is very much a subjective tuning system. You know, I just chose what is typically used in Western composition, and there are lots and lots of different tuning systems, and you know, it may turn out that they are more correlated with chemical shifts than this one. But I felt that this one was the most approachable, at least to start talking about the correlation. As for the difference in background fields, I did gloss over it quickly while we were here. So these filters here and here were constructed with I think it was 500 megahertz for the left and then 200 megahertz for the right. So I did try it for multiple field strengths, and the result is that you just get sort of less of a degree of splitting, and then as a result you get less frequencies that are kept in on the high end, and then it just sounds even more muffled. So that's definitely a consideration that I had throughout the thesis about what information do we lose when we shift up and down in field strength, and that's something I'd like to look into further.
And I have another question. Do we expect any particular notes or kinds of music to be particularly in tune with molecules in general?
Oh, that would be really interesting if we could end up finding something. So one thing I will mention with this research is that it focuses very much on what's called hydrogen NMR. So the idea is typically you work with a particular atom in mind when you're trying to pick up the signal on chemical environments. This is where I was talking about the differences in ethanol. We're specifically looking at how this hydrogen atom is behaving. You could just as easily do the same with carbon atoms or various other molecules, depending on what you're looking at. So there may be a different correlation when we move to carbon versus hydrogen. Lost my train of thought. There was something else I was going to say. No, never mind. Can't remember it. But yeah, so there is a bit of choice about what could be found and what correlation could be made based on what you're looking at. So
fantastic. We have Darren has said that this is so interesting. Please tell me this means that I can figure out which chords will resonate best with the serotonin as opposed to adrenaline.
That is a really good idea. That is really good. I did have a bit of trouble trying to pick what molecule to focus on with the presentation. Someone did suggest caffeine because everyone knows caffeine. Stuck with ethanol mostly because it's a little simpler to look at, but also too, when I was first starting, my supervisor told me that he'd already worked out that ethanol roughly works out to a G minor, like a G minor chord or something like that. So that was sort of my branching off point. But for sure, looking at serotonin, it would be interesting to see what kind of stuff we get from there.
Fantastic. We've also had a few more comments, no specific questions, but Indigo said interesting, also hardware to find, but solid state NMR would be interesting in this space too. Very thought-provoking work. And Jack said that they're hoping to eventually see a suite of symphony music that plays the resonance scene in DNA strands or something similar.
That would be really good too. And this isn't the first time that scientists have tried to correlate music with chemical structure. There was a paper I read about a music professor, a composer who was trying to who composed the music based off of data he received from pigeon DNA used in an NMR spectrometer. It was like a 17-minute long piece, and sort of arbitrarily made a scale based off the data that he was receiving and built a melody out of that, which if anyone's interested, I forget the name of the author, but Google pigeon DNA NMR and you'll probably find it. Interesting read for sure.
Wow, amazing. Thank you so much, Jake. Feel free to have a look at the awesome comments in your in the chat there about your very thought-provoking talk. And thank you, everyone. Please thank Jake again for his great presentation, and all the best with your research.
Thank you very much. Thank you for having me.